Okay, so last time we started section 15.2, and that was the Wilcoxon signed rank test. So before we get rolling too much, remind me what the signed rank test is used for. Say it again. Okay. I'm going to get a blank one of these. So a non-parametric test of what? So the Wilcoxon signed rank test. This is section 15.2. Used for blank. What?
Comparing non-normally distributed data.
Okay. And that's a really general thing for really any non-parametric test is used for that reason. But specifically, when do we use the signed rank test instead of the rank sum test? Paired data. For paired data, when normality is not assumed. So either you know it's not normal, or at least you're not willing to assume that it is, then you would use the Wilcoxon signed rank test. And I gave you last time the method for doing it, right? And I was in the middle of an example about golf scores. Do you remember this? Okay. Unfortunately, the import isn't perfect when I bring it into Active Inspire. I had a PowerPoint presentation, and I used on my computer my little pen, and I circled things, and then when I imported it, the circles are off. They're not circling the right thing, so it's going to get real cluttered. But remember that the scenario that we were doing when we ended last time was a women's golf team. And this is in your book, example 1513 in your book. So if you go either in the paper book or on the e-book, what? Oh, that's right. We don't have chapter 15 in the paper book. It stops at 14. So you're going to be in your e-book, and scroll through till you get to example 1513, and it's about women's golf scores, right? And so it's paired data. So when you go to a golf tournament, you usually play more than one round, right? So they're wondering, do they get better on the second round? That's the question. Do they get better? And so they take the difference. So they take each girl's score in the first round and then the same girl's score in the second round and take the difference. So that's round 2 minus round 1. If they got better, what kind of values would you expect? If it took round 2 minus round 1, and in golf, better means lower score. So you expect a lower score in round 2 minus a bigger score, you're going to get negatives, right? So you'd expect negatives. Now, unfortunately, it didn't occur to me until it was too late. No, wait, I may have. Let me, bear with me just a second, and I'm going to pull up the PowerPoint outside of Active Inspire. And yeah, so I did have it. So this is the example. Oh, I guess it's 1511. I was doing it last time from the old book, and it was example 1513 in the old book. Apparently they've deleted 2 examples. Or moved it up, whatever. But so here's the round 2 scores for 12 women on this team. 94, 85, and so on. And then the round 1 scores are written below because that's the direction they're going to do the subtraction. So we have a 5 and then a -5. So this particular woman actually got worse. Her round 2 score was 5 units higher 5 units, 5 strokes higher than their round 1 score. So that's a positive 5. Then the next one is negative 5, a 2, a negative 6, and so on. Now, do you remember the procedure to do the signed rank test? First of all, what would the null hypothesis be? That the difference is 0. So if the difference was 0, you would expect these differences to be 0. But you know that every once in a while the wind blows and you can blame your stroke on that. And so you're not always going to do exactly the same every round. But it should be random error around 0. So you get about as many positives as you do negatives. The signed rank test kind of compares, well, how many positives did you get and how many negatives did you get? If you get more of one than you would expect, you'd expect about half positive, half negative. If you get more of one than the other, then you start to think, well, that might be significant. Well, just looking at the count of number of negatives, how many negatives are there? 6 out of 12. 6 positives, 6 negatives. So before we ever do the signed rank test, what's your eyeball test saying?
They're the same.
That doesn't seem to improve much. At least not with the sample this small. You're not going to detect that as different, right? This particular woman was 16 strokes better, right? That's a lot. But what do you notice? Think about. Let me start that sentence over. What do you think about doing a paired t-test with this data? Do you think it would be valid? What's the assumption needed for
Size needs to be greater than 30.
sample size needs to be at least 30 or normally distributed. And it's the differences that have to be normally distributed. What do you think?
That's an outlier.
Yeah, we got a big outlier, small sample with a big outlier. You start thinking, maybe it's not normal. Okay. Did you have a question, Jeremy?
Yeah.
Okay.
Sorry. You said something important. I don't want to forget it. Okay.
I wish all students were like
About
that.
the null, the difference is 0, but there it says the scores scores have the same distribution in round 1 and 2.
Right.
So which way do you want us to say this?
This is the appropriate way to say it, that the scores have the same distribution. Remember, we said if you're willing to make an additional assumption, right, that the distributions have the same shape, then it comes down to the median score in the first round would be the same as the median score in the second round, which would say that the difference is 0.
The difference is 0. So
Right.
it's saying the same thing.
Right.
Would you prefer it said in difference is 0, say if this came up on the test, or would you prefer it in that term?
I would give full credit if I say, what's the null hypothesis? You say the null hypothesis is there's no difference.
Okay.
That's fine, right? This is technically a better way to say it, I suppose. But and then the alternative is that scores are systematically lower or higher in round 2. So that's telling me it's a two-tailed test. They're lower or higher, right? Now, what the preconceived idea here is that, well, scores ought to get better because you got to practice it once. Right? You would expect the scores to get better, but here they're not. They didn't word it that way. Okay, so let me go back to this one. And again, I've got pre-circled things in here, and they're in the wrong spots. You know what I might be able to do? Let me go to here. And then I'll have to undo all this in a second, but I want to close that. I'll just write right on this rather than have it inside of Active Inspire. There. So the first step is to get the differences, and then what did we do? You remember? Then you ignore the negatives, but then you rank them lowest to highest, right? And so I might be able to just, yeah, there we go. Ooh, now my circle's lined up. Right? So, what's your question?
It wasn't. I'm just fighting with my eyes.
Oh. So, in the book, this looked better, but when I imported it into PowerPoint, I couldn't tell which ones were bolded and which ones weren't. And so I circled them, right? So the circled ones, the authors had bolded, and they were the ones that came from negative scores. So remember how it works. You get the scores, you strip off the negatives. So you take the absolute values, then you order them and rank them. Right? So there was a positive 5, there was a negative 5, and then later there were 2 more negative 5s. So the ones that are circled were the ones that were negative. Right? Is everybody understanding? So then down here, these are the values put in rank order. So here's a 1, it goes first. Here's a 2, then there's 2 3s, and so on. And then you rank them. So the 1 was the smallest, so it gets rank 1. Then a 2 gets a 2, and a 3 and 3. There's 2 3s, so you give the average rank. So they both get 3.5. And then 4 is by itself, so it's rank 5. And then there's 1, 2, 3, 4. Dang it! Now I have to use the mouse to go backwards, I think. So this is rank 5. This would be 6, 7, 8, 9, 10. So what's the average of those numbers? 6, 7, 8, 9, 10. The average is 8. You can tell by seeing what rank they used. You're using the average of the ranks they would be if they weren't tied. Understand? So they all get an 8. And then you can circle either the positive ones or the negative ones. It doesn't matter. The book calls it W plus, which to me implies we're summing the positive ones, right? But they didn't in this example. They summed the negative ones. So if you sum all the ones I circled, what do you get? Well, you get 50.5, right? So when you look at this example in the book, it's going to say W plus is 50.5. Now, if you sum the ones that are positive, the ones that aren't circled, what do you get?
Can I ask a question?
Sure.
Where did you get the 3.5? Like the rank 3.5?
My ranks, right? So this would be rank 1, 2, 3, 4. These are tied, so you're averaging 3 and 4 to get 3.5. Good question. Okay? So if I sum the ones that aren't circled, the ranks down here that aren't circled, 1 and 2 is 3, plus 3.5 is 6.5, plus 8 is... yeah, it's not the answer I was aiming for. How do I want to say it? Let me do it again. 6.5 plus 16, right? Because I got 2 8s that aren't circled. 22.5. I was looking for the number 11. What did I do with my notebook? Here it is. I was looking for the number 11.5 because that ends up being what SAS gives, and so I may have just added quickly in my head and said, "Oh yeah, that's where SAS got their number." I was challenged, still am, and I'll show you why, to mimic this completely in SAS. And the SAS help says, well, they handle things a little different than the way Wilcoxon first did it, because somebody later published a paper that shows a better example.
Lost your camera.
Oh, thank you. But let's do it. If I add the positives, right? So the book got this 50.5. If I add, so I'm going to change that to a negative because it summed the negative ones. And remember, we said it's arbitrary. You could do either one. You said 22.5?
Correct.
Okay. So if you add the positives, you get 22.5. Now, what would the mean of W positive be? Do you remember that formula? I gave it to you last time. It was N times N plus 1 divided by 4. And what do you get when you do that? N is number of pairs. So that's a 12. So you get 12 times 13 divided by 4.
39.
39. Okay? So this is equal to 39.
That's the difference is 11.5.
From 39 minus that,
39 minus 50.5.
if you take, 39 minus 50.5, you get negative 11.5. That's right. And what do you get if you take 39 minus 22.5?
16.5.
16.5. That's not the answer I was hoping for. I was hoping for the positive 11.5 because it seems like 39 should be halfway between those, right? But if I take 39 minus the 50.5, you get negative 11.5. So let me flip out of this and go over to SAS. Well, let's redo. Right? So that one is not. Now if we add the ones that aren't circled, that one would
There's the 5 difference.
yeah, that's the 5 difference because it had a rank of 5. So instead of 16.5, we should get 11.5. And this you can't, with this not being white behind there, you can't really see it, but that's right here. That should be 11.5. All right, so now they are centered around 39. Sorry to have killed all the time figuring that out, but
5 is going to change too there.
no, the 50.5 was right because I didn't do that one. I just circled their answer,
The 22,
and they did it right.
the 22.5 is going to be 27.5 instead of what we computed for the W negative.
Yeah, the W.
So that
The W positive. If you add up the negative ones that were circled, you should get 50.5 because that's what they did, and I'm assuming they didn't make a mistake. Now this, I wrote 11.5, but that should be 27.5, and it's the difference from 39 that is now 11.5. Okay? Okay. Now, let's go back to the SAS output. And if I do this, I think I can get rid of all that stuff. Here is the signed rank test, right? So the signed rank test says that the test statistic is negative 11.5. Now we got a W plus and a W minus, and neither one of them were negative 11.5. So what is SAS doing?
We got one of them to be negative 11.5.
Well, actually we got a 27.5 and we got a 50.5. But if you subtract the 39, right? So when SAS is forming the test statistic, they're taking 27.5 minus 39, right? To get a negative 11.5. They're saying, so we got the sum of the ones that were positive. That, because the book did the negatives and got 50.5. It really doesn't matter because it's just it's a two-tailed test, so it's which tail you're in. But SAS is doing it as the sum of the ones that were positive, subtracting the expected value of the sum if the null is true, which was a 39. So mu sub W, right? So 27.5 minus 39 gives you negative 11.5. And then it gives a p-value, 3877, 0.3877. Okay? So, before we talk about this p-value, what's the conclusion from it?
Failing to reject the null.
Failing to reject the null, so...
They have the same
Okay. We do not have sufficient evidence to say there is a difference in the distributions. So in everyday language, we don't have enough evidence from this sample to say that the scores change from round 1 to round 2. The scores seem to be within random fluctuation of what you would expect if there's no difference. Okay? So now let me go over to SAS and show how this is run. And before I do, notice the title up here, the second line, the univariate procedure. And the distribution analysis of the variable name is diff. Okay? So let me go to SAS now. And here is the data. And so I have a spreadsheet with columns for the different variables. So this is just player number 1 through 12. And then their round 1 score, their round 2 score, and then I had to create a variable called diff. Right? I can show you how. It's pretty easy to do within SAS Enterprise. You have to go over here to edit, unprotect the data file, add a column, and so on. And it's fairly easy, but to be honest, it's easier to do it in Excel first than read it in there with your diff variable already created. It's a little bit easier. But anyway, it's the diff variable that we analyze. The rest we completely ignore. So to do the analysis, start with tasks. Any guesses? If we go to multivariate or regression or ANOVA, it's going to be expecting more than one group, right? So it is under describe, which throws me because I don't usually go there to do tests. But it is under describe, and then distribution analysis. And a little bit of a hint that it might be there because that's the null hypothesis worded the exactly correct way. The distributions are the same. So we're going to analyze the distributions. So distribution analysis. Now I'll show you the code behind the scenes here because it lets us see that. But other than that, you don't know that this is that univariate procedure that was on the SAS output. But so I want to take the diff variable and I want to put it into analysis variable. The rest of the variables, round 2, round 1, and player, we're just going to ignore. So I don't have to do anything else here. And then under distributions, there's all this stuff. I can get summary statistics. That's by default anyway. and then I can test for different distributions. But I'm not interested in that. All I want to know is I want the Wilcoxon signed rank test for whether the differences are 0 or not. So I'm going to click on let's see, tables, I think it is. Did I not get it clicked? Yeah, there we go. And the default, there's all these things that you can ask for. The default 3 that are pre-selected are basic confidence intervals. So you can ask for basic confidence intervals on that diff variable. That's fine. Basic measures, and then tests for location. Ooh, what does that mean? The word test sounds promising because I want to do a test, but what is location? It's like on the number line, where is the center of the distribution located, right? So in higher level statistics, you'll hear them talk about that's a scale parameter, that's a location parameter. So location parameters are what we call in MA343 measures of center. Mean, median, mode, those are location parameters. Where on the number line is your distribution? Scale parameters, what would be a scale parameter? Hint, scale tells you the spread. So what are our measures of spread? Standard deviation, intraquartile range, variance, all those things are scale parameters. Right? So I want test for location, and you can set confidence levels if you want them to be different. That's pretty typical. And then we don't get, there's nothing in here that says Wilcoxon signed rank test. So you just have to know that it's in this procedure. This is where you find it. You can go to the help, and it'll pull up the SAS help menu, and you can search for Wilcoxon signed rank, and it'll tell you. You do it in Proc Univariate, and it'll explain, but it takes a little while to get through all that. So here's the output that we were just looking at. Okay, so down here, tests for location, it says mu0 equals 0. Right? What the heck does that mean? That's the null hypothesis. Mu0 is sub-zero hypothesis, right? So the null hypothesized value of the mean difference is 0. And they write it that way in a generic sense because technically, remember, the signed rank test isn't testing the mean is 0. It's testing more the median is 0 or just that the distributions are the same. But they write it this way to apply to all tests. So it gives us a student's t-test. What would that test be? Yeah, but I mean, what's that test called? The student's t test for difference equals 0. That's called the paired t-test. So that's given by default. You get the paired t-test. Then you get this sign test. And the sign test is not very popular. You won't see people using it much. And it literally, all it does is count how many positives did you get and how many negatives did you get. It's a test of the sign of the differences, right? And look at its p-value, a 1. So it's not a very powerful test. The signed rank test, that's the Wilcoxon signed rank test. There's the value of the test statistic, negative 11.5, which was the 27.5 minus 39. And then to compute the probability of that, they then do basically form a test statistic out of that number by dividing by its variance and using a normal approximation to it. And this number, I had to look it up, but this number is actually a t approximation. So they use the t distribution for small samples instead of normal. But it's not, our book doesn't even go into that. But So p-value of 0.3877. Okay, that's the signed rank test. So if I flip back over to the example in the book, oops. Oh, I guess I didn't make a slide out of it. He's got in that example in the book, which I have not logged on to the ebook, but he shows, he's got a little bit of an output where he shows, here's what you get if you do it in SAS, and it matches that 0.38. He rounds to 3 decimals, so it's like 0.389 or 388 or whatever it was. Yeah, 388. But then he's got, oh, if you do it in Minitab, and it's not exactly the same p-value. It's real close. It's like 0.38 something else. And then he's got several different packages, and they all have slightly different values. That's because behind the scenes, SAS is using a slightly different formula to compute the variance and so on. And, you know, that's kind of beyond the scope of this book, and discussing why one package uses one formula and another package uses a different one. It's just the people that wrote the package, reading the literature, decided this is the one that's most common or whatever. Lots of options for these approximate tests. Okay, any questions about signed rank test? All right, the only thing left in chapter 15 for us is the signed rank test. Oops, that's not what I wanted to do. I'm sorry, not the signed rank test, the Kruskal-Wallis test. And let's see, I gotta do that. So I told you before what the Kruskal-Wallis test is used for. Do you remember? Give you a hint.
Non-parametric one-way ANOVA.
Right. Good. Non-parametric one-way ANOVA. So it does the same thing for the Wilcoxon-Rank sum test that ANOVA, parametric ANOVA, does for the t-test. It just expands to more than 2 groups, right? So more than 2 groups. So, just like we've been doing, the null and the alternative hypotheses are really best written out as sentences rather than using Greek letters and all that. Let's say we have response variable y. Then the easiest way to write the null hypothesis is that the response variable y has the same distribution in all groups. Now, do you remember in one-way ANOVA, we're going to borrow some of that notation. In one-way ANOVA, you have one factor, but it has multiple levels, right? And we used a capital I for the number of levels. So that's the number of groups, basically, right? So it has the same distribution in all capital I groups. So guess what the alternative is? The distribution is not the same in all I groups. So at least one of the groups has a different distribution. Typically, it's the center of that distribution that we're detecting to be different. Y has Y has a different distribution in at least one of the I groups. Okay, has everybody got what they want on here? So to do the Kruskal-Wallis test, it's similar to what we did for the Wilcoxon rank sum test. You remember what that was? What did we do for the rank sum test? We only had two groups, so we ignored groups and we ranked them, and then we circled which one came from group A or group 1 or whatever, and then summed the ranks for that chosen group. And we said it's arbitrary which group you choose. Well, now you got more than two groups, so you deal with all groups. You get a rank sum for each of the I groups. Okay, so let's get a new page. You rank all capital N observations. Remember, capital N is the grand total, pooling all the groups together. So rank all N observations and so that capital N is the sum of the NI's. And that sum goes from little I equal 1 to capital I. So it's just the grand total. Then we let R sub I be the sum of the ranks in the ith group. So sum of the ranks in ith group. So R little ri is yeah, I strayed from my notes on notation here. I'm using an I badly. Do you see my problem? I've got an I as an index to a summation, and I have an I out there. So this should be a J or some other letter. So I'm going to fix that. So J, and then J equals 1 to N I. Can you read those with this marker? It's hard to make it fine, but so it's the rank sum. Rank of each. That should be a J. RJ is the rank of jth observation in ith group.
So that would be ith group up there.
Yes, it's the ith group, and then we're summing the J through. We're summing the NI ranks in that group. All the rules about using an average for the ties and all that still apply. So you're going to rank, you're going to order them, ignoring what group they're in, but then pick all the ones that came from group 1, sum their ranks. Take all the ones that came from group 2, sum their ranks. All the ones from group 3, sum their ranks. So you get these different, you get a total of capital I of these R's, right? The Kruskal-Wallis statistic, then, they label H, you know, H for Kruskal-Wallis. I don't know where the H came from. And I won't do the derivation of this for you. It's tedious, but that's the coefficient out front, and then you have a summation, and that summation will go little I equal 1 to capital I. So I'm summing across all the groups. I'm summing all of these capital R's. I need to get some stray dots here I need to get rid of. And then it's Ri squared over Ni minus 3 times capital N plus 1. I was just going to say, that's pretty ugly, isn't it? And you may wonder, well, how come they're squaring those R's? Well, if they weren't squared, you'd get something that was approximately normally distributed. If you square a normal, you get a chi-square. So this thing is a simpler version. If you do it in the square and get a chi-square, it's a little easier to do the math. So this thing is distributed. Have I used that symbol in here before?
I think so.
Yeah. Some of you shook your head no, and some nodded yes. But this is approximately chi-square with capital I minus 1 degrees of freedom. So I write that in a parentheses. Chi-square, I don't draw a really pretty chi, but that's the Greek letter chi squared, and then this is degrees of freedom. Right? So it's approximately chi-squared if null is true. Which is how we always do test statistics. We find their distribution if the null is true. Then we can use that to compute a p-value. Given the null is true, here's the probability of getting data like you got. Okay? Okay? Now, again, just like the Wilcoxon rank sum test, if you make an assumption about the distributions of these capital I groups, and you're willing to assume that all of those have the same shape, just different locations, then you're testing, is there a difference in the medians between these groups? Whereas ANOVA, regular ANOVA, would test, is there a difference in the means of these groups? But without making that additional assumption, then the way we wrote the null a minute ago is the best you can say, that they all have the same distribution versus one of them has a different distribution. Looks like I ran out of time, so I don't have time to do an example where we'll fill in numbers, so we'll do that on Monday. We got an example out of the book where we'll have a y variable that we can then rank and do all that and come up with these rank sums. So we'll do that on Wednesday, and on Monday we'll run it in SAS also. Have a great weekend.